Welcome to Lecture 4.3, Partially Ordered Sets. Let's begin by recalling the definition of a partial order, which we first saw when we learned about binary relations a few lectures ago. A partial order on a set P is a relation that we write sometimes like less than or equal to, or some variant of that is reflexive, transitive, and anti-symmetric. Let's recall what that means. Reflexive means that x is less than or equal to itself. Transitive means that if x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z. And anti-symmetric means that if x is less than or equal to y, and y is less than or equal to x, then x and y must be the same. In this case, we say that P is a partially ordered set, or a poset for short. So we slightly abuse notation by saying that P is the partially ordered set, and sometimes that the ordered pair P with the relation is. And that said, sometimes a lot of sources are just going to use plain old less than or equal to instead of the squiggly version. And I think that's okay, because if you think of it from a computer science perspective, you can overload an operator, like less than. For example, we know what less than or equal to means for integers and for floats and for other data types, so we can define what it means, say, for a collection of subsets or a collection of partitions, and get away with that as well. But that said, because for me, when I'm typesetting this lecture, it's just as easy for me to write a little squiggly less than or equal to sign. I'll usually stick with that. Here's another way to define a partially ordered set. We can do it by a strict partial order on P. And this is a relation that is analogous to a strict less than symbol. So this is irreflexive, which means that x is not related to itself. Transitive, you know what that means. And anti-symmetric for a strict partial order means that if x is strictly less than y, then y is not strictly less than x. Finally, there is a special case of a poset that I want to define, and that occurs when, for every pair of elements A and B that are distinct, either A is less than or equal to B, or B is less than or equal to A. In that case, we call P a totally ordered set. At this point, I will give you a bunch of definitions, and though it may seem like information overload, I think most of these definitions are fairly intuitive just from the name. So let's begin. Suppose P is a poset, and throughout I'm going to let lowercase letters like A, X, Y, and Z be elements in P. First, if x is not less than or equal to y, and y is not less than or equal to x, then x and y are incomparable. Otherwise, they are comparable. And I'm going to go through a few definitions before I give an example. If x is less than or equal to z, but there is not a y that's strictly between these two, then we say that z covers x. If A is in P, but there is not an element in P strictly less than A, then we say A is a minimal element. A similar concept is that of a minimum element. And this is an element that is smaller than everything. So if A is less than or equal to x for all x in P, we say that A is the minimum element, and emphasize the versus A. We can only have one minimum element, but we could have many minimal elements. And again, I'm going to give an example shortly. If Z is in P, but there is not an X in P that is strictly bigger than Z, then we say Z is a maximal element. And of course, what's coming next is the definition of a maximum element, which intuitively is an element which is bigger than everything. So if x is less than or equal to z for all x in P, then we say x is the maximum element. Okay, so let me give you some definitions. Let's see, I'm going to just draw a poset. This is a common way to draw a poset where things are arranged vertically to mean they are comparable. So I don't know, do I want to give names? Yeah, let me give A, B, C, D, E, F, G, H, and then let me do I and J, and then I'll do K. So what I will do is anytime 2 points are connected by a line, that means that, or a line that goes upwards, that means that one of them is smaller than the other. So let's see, how do I want to do that? Yeah, let's just do that. So here's a poset, and the fact that A is below B means that A is less than or equal to B. However, A and E are incomparable because there is no upward path going from A to E. So comparable elements, any two elements that are connected via some path that goes upward. So D is less than or equal to B, and B is less than or equal to C. So by transitivity, D is less than or equal to C. So D and C are comparable, but B and F are incomparable. K is incomparable to everything other than itself. Everything is comparable to itself. That's the reflexive property. Okay, so what about this? Covering relations. So if we have two elements, X and Z, and there's nothing between them, then Z covers X. So the covering relations are given precisely by these edges. So H covers E, C covers B, B covers D. Okay, what about minimal elements? I'm going to use red for this. So a minimal element is an element such that there is nothing that's below it. So minimal elements are going to be the ones that are at the bottom. A, D, G, I, and K. What about a minimum element? A minimum element is something such that everything in the poset is bigger than. So there's not going to be any one of those. So there would have to be some element such that everything else is above it, and that's obviously not the case. So what about a maximum element, or a maximal element? So maximal elements are the ones that are at top. So C is maximal, F is maximal, H, J, and K is maximal. And there are no maximum elements, because for that there would have to be something that everything is below. Now, if we were to make a maximum element, we could do that by adding an element here and connecting it to, say, everything else. If we did that, now, okay, let's call this L. L would be a maximum element, although we would have to, then K would no longer be maximal. Let me do a very different example now. So let's consider something like, say, the real numbers, and just the standard less than or equal to. That is a poset. It is an infinite poset. And let's think about which of these definitions apply. So first of all, this is what's called a total order from the previous slide, because everything is comparable, or any pair of elements are comparable. There are no covering relations, because for any two real numbers, there's something in between it. There are no minimal elements, right? Because for every real number, there's something smaller. So there's no minimum elements either. And similarly, there are no maximal elements or maximum elements. It's a good exercise to prove that a minimum element must be minimal and a maximum element must be maximal. Okay, let's move on. I got some more definitions that I'm going to squeeze down here at the bottom. A chain in a poset is a subset, C, such that any two elements are comparable. So going back to our previous example, I think this is the previous example, it doesn't really matter. Something like this, and I don't care about the other stuff. Any element is in a chain by itself. A size 2 chain is a collection of elements such that they are comparable. So there's an example of a size 2 chain. I can throw in this element, and now I have a size 3 chain. These elements are all comparable pairwise. And then in this example, that's all I can do. There's not going to be a larger chain. There are other chains. For example, this is a size 2 chain right there. This is a size 3 chain. And also, notice that any subset of a chain is clearly going to be a chain as well. Next, an anti-chain in a poset is a subset of incomparable elements. I'm going to hold off for examples until I finish this slide. I'm almost done. Next, we come to the definition of what it means for one poset to be an extension of another one. And let me explain my notation here. We have two posets, one of them is P and one of them is P prime. And in general, we can't expect them to have the same ordering relation. And since there aren't too many of these less than or equal to options, one convenient way to do that is to just use a standard less than or equal to, or the squiggly one, and put as a subscript the set itself. So this just means the order relation in P, and this is the order relation in P prime. So we say that a poset P prime is an extension of P if they have the same underlying base set. I know I could have written P for both, but I still like this. And if A being less than or equal to B in P implies that A is less than or equal to B in P prime. I know that's a mouthful, but let's do an example, and I think it should be clear about what I mean by this. So let's suppose that we have a simple 4-element poset. Let me call this A, B, C, and D. So here, A is not comparable to B, and C is not comparable to D. So this is a poset. A is less than C, A is less than D, B is less than C, and B is less than D. So an extension just means that anytime that you have an edge over here, well, first of all, an extension is going to be on the same underlying set. Let me just give you an example. So if I do this, so if I add an edge, so here I added this edge right here, now I'm declaring that A is also less than B. And I should probably label these with the same A, B, C, D. So an extension just means you have at least as many relations here in P prime as you do in P. So of course another extension is A, B, C, D. So A, B, C, D. This is what we call a linear extension because this is a total order. And notice that I actually have I've drawn fewer edges here than I have here, but that's because by transitivity, I don't need to draw edges like A to C, A to D, and B to D, though they are there. So here we have P, here we have P prime, and here we have P double prime. So P prime is an extension of P, and P double prime is an extension of P prime. So an extension just means we have at least as many relations. And finally, here's something that I mentioned. A linear extension of a poset is an extension that is a total order. And let me emphasize that there's often many linear extensions. So let me do that same example that I did before. So this is A, B, C, D. So one linear extension is that I could do A before B and then C before D. So let's see, so A, B, C, D. There's one possible linear extension, but of course there's no reason I have to put A first. I could put B first. So I could do B, then A, then C, then D. But also C and D, I could choose to do those in a different order. So I could do A, B, D, C. And then finally, I could do B, A, D, C. So all four of these are linear extensions of this poset. And you can think of this as a way to flatten this poset. So you sort of squish this together with that. Sometimes I have heard these things called flattenings of posets as well. So you have to decide whether A is going to go above or below B, and whether C is going to go above and below D. That we have the restriction that A always has to be below C, and B has to be below D. I will now go through a number of examples. Some of these will be familiar from the lecture on binary relations, and others will be new. I will also try to incorporate some of the definitions on the previous slide into these examples. We'll start with the power set. So given a fixed set S, finite or infinite, we can look at the set of all subsets and define a poset by subset inclusion. In other words, we say that A is less than or equal to B if and only if it is a subset of B. Here is an example where the set S is the three-element set containing A, B, and C. So there is clearly only one minimal element, the empty set, and that is also the minimum element, and one maximal element, S, which is also the maximum. What else can we say about this? The longest chain has length 4, starting at the empty set. Any path from there up to the top, say, for example, the empty set A, AC, and ABC, that is a chain of length 4. Any subset of that has length is a chain. What else can we say? This poset is said to have height 4 because that is the length of the longest chain. I didn't define that formally, but it's worth just mentioning it. Something else is it is said to have width 3 because the size of the largest anti-chain has size 3. For example, AB, AC, and BC are all incomparable elements. It's not the only one. The singletons A, B, and C are also a size 3 anti-chain. Of course, you can mix and match. A and BC form an anti-chain. And what else do I want to say about that? So what about an extension? Well, just for fun, it doesn't really make any sense, but you could certainly declare B to be a subset of AC. For example, you could define a new relation where A is less than or equal to B if and only if the size of A is less than or equal to the size of B. I think this is the only missing, no, it's not quite the only missing edge. So for there, I would have to add an edge from A to BC and from C to AB. And if we did that, we get a new poset, which is an extension of the power set poset. It is not a linear extension, though, because we still have things like A is incomparable with B. Here is another example that we have seen before. This is the poset of partitions of an n-element set. The order relation is called refinement, and here's what that means. If you have a partition with blocks, so in this example, 1 and 2, 3, 4 are the blocks. You can visually see it over here, or I guess these things don't line up exactly. Then if I take a block and I break it up into smaller pieces, I get a more refined partition. And so that's going to be the relation. For example, if I take 2, 3, 4 and I chop it up into a 2, 3, and a 4, I get a partition that is below it or less than it. I could also chop 2, 3, 4 into 2, 4, and 3, or into 2 and 3, 4, or I could fully chop it up into 1, 2, 3, 4 down here. So this poset has one minimal element that has 4 size 1 blocks, which is also the minimum, and it has one maximal element, which has one size 4 block, which is also the maximum, because it is above everything. This poset has height 4 because the length of the longest chain is size 4, and it has width 7 because there is a size 7 anti-chain, that is 7 elements that are all mutually incomparable. This poset has a nice sense of what level. This is I'm going to call this level 0. These partitions have level 1, these have level 2, and these have level 3. This is sometimes called a graded poset. I will not define it, but basically it means that there's a nice notion of levels. An example of a non-graded poset would be something like, I'll just draw the diagram, something like that. It's not clear if this has height 1 or height 2, because so this is a non-graded poset. Okay, so going back to this one, one more thing I want to point out about this. You don't need to know this, but it's worth mentioning, is that this is something called a lattice. You've likely heard the term lattice thrown around, but formally a lattice is a poset with some extra properties. And basically what those properties are is you can think of them as analogous to the existence of a unique greatest common divisor and least common multiple. So I think I'll just show this to you with an example. Let me call this partition here 1, 2, 3, 4. Let me call this, let me see, I'll call it P, and I'll call this one over here 1, 2, 3, 4. I'll call it Q. Then the least common multiple of these, or two elements, are said to have a least common multiple if there is some partition, if there's a unique minimal partition, not minimal in the whole poset, but let me say it this way, of all of the partitions that are above both of these, let's see what there are. So there's this 1, 2, 3, 4, and 1, 2, 3, 4. Of all of those, there is a unique minimal one, and indeed there is. So this is said to be, so sometimes we write this as P, and then we use that OR symbol, or Q, and we call this the join of P and Q, which I think is a horrible name. I think it should just be called the least common multiple. I think is fine. So let me write that down, that this is the join. Another thing people call it is, these things are called upper bounds of P and Q, and this is the least upper bound. And not all posets have a least upper bound. Some posets will have multiple upper bounds, and there might be 2 minimal ones, but this is not the case. P and Q also have a greatest lower bound. So if you look at everything that is below P and Q, well, here you only have one element. And so this is called, sometimes it's written P and Q. The same symbol is used, although we don't say and this is called a meet. So this is a greatest lower bound, and the join is a least upper bound. And upper bounds may or may not exist in all posets, and there may not be a least upper bound. If the poset's infinite, there may not be the set of upper bounds may not have a least element, or a minimal one might not be unique. There might be multiple ones. Let's do another one just for practice. So let's take, let me call this P prime, and let me call this Q prime. So P prime is 1, 4, 2, and 3, and Q prime is 1, 2, 3, 4. So the join of P and Q it has to be up here, the maximum element, and the meet has to be down here, the minimum element. Let me actually do one more, because that was pretty trivial. The join had to be above both, and the meet had to be below both. Let me pick 2 on the same level. So I'm going to do 1, 2, 4, and 3, and 1, 3, 2, and 4. Here, the join of this, there is nothing that covers both, so we have to go all the way up to the top for the join, and for the meet, we need to go down to the bottom. Okay, so I don't remember if I said this. A lattice is a poset such that every pair of elements has a meet and has a join, has a unique greatest lower bound and unique least upper bound. And I guess by saying greatest and least, we are implying that they are unique. Our third example is any acyclic directed graph. Up until now, I've been writing most of my posets vertically. And when I do this, it's implied that the relation is given by any vertical path. So in other words, if there's a vertical path from A to B, then A is less than or equal to B. And because of this, I don't need to draw orientations on my edges. For example, this diagram is redundant because we don't need the arrow tips to describe the ordering. However, we're talking about acyclic directed graphs. So the point here is that any acyclic directed graph describes a poset. So let me just give you an example. So here's an example. I'm doing an orientation of a hexagon, A, B, C, D, E, F. So this describes a poset, and namely x is less than or equal to y if there exists not an edge but a directed path from x to y. And the fact that it's acyclic means that there is no directed cycle, and that is important because if we have a directed cycle, we lose the anti-symmetric property, and it's not a partial order. So I may not need or want to draw this poset vertically, and I mean let's do it just for fun. So A and E are the minimal elements; those are the sources. The maximal elements are F and E. So let's see. So I have F here. I have B here. Both of these things are bigger than A. F is bigger than E. Then I also have D here, and then what else do I have? I guess I'm missing a C. So C, I have something like, oh, I guess I don't need the arrows. Something like that. Okay, the last thing I want to say is sometimes we have a poset that looks abstract, like what could these things refer to other than just arbitrary, like a toy example. But sometimes there's something behind the scenes that's not so obvious. I'm tempted to say pause the video and see if you can figure out something that this might describe, but I think that might be a little too out there. So let me just show you. Here is an example of a stack of objects. I was going to say balls, but then there's this thing here. And let's say that some object is less, so let's say that x is less than or equal to y if and only if y lies, if y is exerting weight on x. So if I is exerting weight on C, so I think it should be easy to see why the poset here for these balls is described by this directed graph right here. Finally, the last thing I want to say about acyclic directed graphs, maybe I should have said it earlier, is that sometimes we're given a graph and that describes a poset, and it may have extra edges, and that's okay. So for example, if we're going to draw these things vertically, A, B, C, D, we don't need this last edge from A to D. But sometimes if you're given a graph, it maybe came from a different purpose, and so we have those extra edges in there, and that's fine. Here's another example that we have seen before. Partial orders where the relation is divisibility. We can look at a fixed integer n and look at its, well, really positive divisors. Or we can look at the positive integers. That's going to be an infinite poset. And here I really, in both cases, want to just look at positive numbers, because if we have something like
n that divides negative n, then negative n divides n itself, and then we lose anti-symmetry. Let me do an example. Here is n equals 60. Let me say a few words about this poset. First of all, it has height 5 because the length of a longest chain is 1, 2, 3, 4, 5. It has width 4 because here's an anti-chain of size 4. What else can we say about this? Let me illustrate the concept of a GCD and LCM in this example. So let's take see what's a good example. How about 2 and 15? So the least common multiple is, if you look at the set of all things that are above both of these, there's 30 and there is 60. And there's going to be, of course, a minimal one of those. And then the greatest common divisor is, of everything that's below 2 and 15, well, there's only one of them, it's going to be that one. So again, the LCM is a example of a least upper bound, and the GCD is an example of a greatest lower bound. Our fifth example, I don't think we've seen this before, vertices in a rooted tree. For example, a computer directory structure or a family tree. So by computer directory structure, consider the following. You don't usually draw it this way, but I think you'll get the idea. So if you use Unix, you'll recognize this especially. So within the root directory, or just a slash, there's bin, there's user, there might be users, there might be lib or library. Within users, there might be students, and there might be faculty, and then there might be staff, and maybe within a student, maybe there might be Alice, there might be Bob, within Alice there might be desktop, and there might be downloads. And of course, a lot more than this. But it should get the idea that we can say that one of these folders or directories is less than or equal to another one if it is contained, if it's a subfolder of it. So desktop is a subfolder of users, not a direct subfolder obviously, but desktop and staff are incomparable. So Alice and faculty are incomparable. And now, in stark contrast with the previous example of computer directory structure, here is an example of a family tree. So we can put a natural partial order in this by saying that x is less than or equal to y if and only if x is a direct descendant of y. So for example, Rob is less than or equal to Rickard, but Rob and Brandon are incomparable. Our last example involves strongly connected components in a directed graph. I think this is best done by an example. So let me just draw some vertices. I'm just making this up as we go along. And I'll draw some edges. I'll use a different color for the edges. Okay, so maybe something like this. Let me make that a double edge. Okay, so here's our example. A strongly connected component is a subset of vertices such that, a maximal subset of vertices such that you can get from any one vertex to any other vertex via a directed path. So this 3 cycle is a, let's see, so in this cycle, this collection of vertices you can get from one to any other via a directed path. But look, there's actually a bigger cycle that contains this. And so these, what is this, 6 vertices are in a strongly connected component, because I don't think any other vertices can communicate with these 6 both forward and backwards. So let me draw that. So now what else is there? This vertex is a sink. This vertex cannot reach any other vertex, so it has to be in a strongly connected component with itself. And this vertex here, it can get to this vertex can get to another one, but you can't get back. So, and also you can get from here to this vertex, but you can't get back into that component. So this is a strongly connected component. And then what else do we have over here? So here we have a two-cycle. These two vertices talk, I'm just going to call them, I'm going to say they talk to each other. And you can get, let's see, you can't ever leave these two vertices. There's nowhere else you can go. So this is another strongly connected component. So anytime you have a directed graph, there's typically going to be cycles, so it's not going to be a poset. But if you isolate the strongly connected components, and now let me give them labels. So I'm going to call this one C1. I'll call this one C2, C3, and C4. These things form a partially ordered set themselves. So C1, C2, C3, C4. Let's see, I can get from C1 to C2 multiple ways, but it doesn't matter. C1 to C2. I can get from C1 to C3, so I'm going to put an edge from C1 to C3. And I can get from C1 to C4, so I'll put an edge from C1 to C4. And I can get from C3 to C4 as well. And I'll put an edge like that. So this describes a partially ordered set. And this works for any directed graph. The strongly connected components determine a directed graph, which in turn determines a poset. Notice if there was a cycle in here somewhere, then that means that the components that I had were not maximal, and I can merge them in here and get rid of, and that would lead to fewer vertices in here and no cycle. So let me show you two more pictures of this that are drawn more professionally than these. These are from Wikipedia. So here's a directed graph with 8 vertices, and these strongly connected components are highlighted. So here's a 3-cycle, here's a 2-cycle, and here's a set of 3 vertices. It's two cycles. Point is you can get from any one of these to any other one of these. And so just for practice, let's look at let's consider the poset of strongly connected components. So I'm going to call this one C1, C2, and C3. So here are let me use a better pen for this. So here's C1, C2, and C3. And I can get from C1 to C2. I can get from C2 to C3 multiple ways. And then I can get from C1 to C3. So here is a directed graph. And we saw earlier how any acyclic directed graph determines a poset. Okay, our second example is right here. So in the blue and black, the blue vertices and black edges are a directed graph, and the strongly connected components are already highlighted, and the arrows correspond to which components you can reach from other components. And so the yellow, if you just look at the yellow nodes and arrows, that determines an acyclic directed graph, and that in turn determines a poset. Finally, I want to conclude this lecture with an application of partially ordered sets to scheduling problems. This comes from the field of operations research, which deals with methods like algorithms, optimization, heuristics, and so forth that improve complex decision making. Operations research is sort of between math and computer science and industrial engineering, sometimes in management science in a business school. And it deals with problems that we often just take for granted, which we don't realize how complex they are. For example, when you book a plane ticket that has 2 or 3 legs, you don't stop to think about it, how hard it is. There are tens of thousands of flights every day, say across the United States or across Europe. And the companies don't want those flights to be empty. They don't want them to be overbooked. They don't want people to wait for 6 hours, and they don't want them to miss their flights. So how to schedule air traffic routes so this works and so you don't waste money is a huge mathematical problem, and it's about complex decision making. Back in the 1950s, The so-called Program Evaluation and Review Technique, or PERT for short, was developed by the United States Navy when they were building the Polaris submarine. In fact, a lot of origins to operations research problems can be traced back to military research, especially around the time of World War II. Also around this time, the critical path method, or CPM for short, was developed by the DuPont Chemical Company for scheduling maintenance. And it was with another company that has since been bought up. I don't remember what they were called. This method was later used during the construction of the World Trade Center. Let me give you an example of what a simple problem might look like. All of these are scheduling problems. In this example from Wikipedia, there are 5 milestones. They call them 10, 20, 30, 40, 50. I would prefer maybe V1, V2, V3, V4, V5, but that's okay. And in this case, we label the edges with durations, how long it takes to go from this milestone to that milestone, maybe using this technique. So this edge, so this takes 4 months. If you go from this 10 to 30, it takes 3 months. If you go this route, it takes 1 month, and so forth. And the goal is typically to see how quickly, how efficiently can you do all these tasks. Can you get through all these milestones? So in this example, the longest path, sort of the critical bottleneck, it's actually called a critical path, is from 10 to 20 to 30. This is 4 months plus 3 months, so that takes 7 months. And there's another path, 3 months, 1 month, 3 month as well. So you're not going to be able to do this in less than 7 months. So this is an example of where the edges are labeled with durations, but there's many other applications where the vertices are labeled with durations. Now, in both PERT and CPM, the set of scheduled tasks form a partially ordered set. As I showed you before, the tasks are labeled with the duration that they take to complete, either at the nodes or the edges, depending on the application. In both of these, the shortest possible completion time is given by some sort of maximal chain through the poset called a critical path. So I'm going to do an example. This one is from Susanna Epp's wonderful book on discrete mathematics. So suppose you have I'm going to call this one task 1. This is task 2. Let's say that task 3 is down here. Let's put task 4 up here. Let's put task 5 here. Let's put task 6 here. Let's put task 7 up here. Let's put task 8 here. And let's put task 9 over here. And now let me put durations for how long these things take. Let's suppose that task 1 takes 7 hours. Actually, before I do that, let me put the restrictions about the order that these things have to be done in. So each edge from one task to another tells you that the task on the left has to be done before the task on the right. So this means that task 2 has to be done after task 1, and task 5 has to be done after task 2 and task 3 and before task 8, but it doesn't matter whether it's done before or after task 4 or task 6. So suppose that task 1 takes 7 hours, task 2 takes 6 hours, task 3 takes 3 hours, task 4 takes 6 hours, task 5 takes 3 hours, task 7 takes 1 hour, that's task 6, task 7 takes 1 hour, task 2 takes 2 hours, and task 9 takes 5 hours. You want to know how long does it take to finish all of these tasks. And of course, there's many variations of this. Maybe you can only do 2 tasks at once. I mean, maybe you have some number of processors. But here we're just going to start with the first one. I'll just give you an example. Start with the first one. This takes 7 hours, so by the time you finish it, you must be 7 hours through. Task 2 takes 6 hours, so by the time you finish task 2, you must be 7 hours in here plus 6 hours, so that's 13 hours. Task 3 takes 3 hours, so you start here, spend 7 hours in task 1, and it takes you 3 more to finish task 3, that's 10 hours. And then task 5 has to be done after task 2, so you can't start on this for 13 hours. But it also has to be done after task 3, but that's okay. This one finishes with time to spare. So this one is you won't be able to finish this until 16 hours in because you got to finish this one here, and it takes 13 hours to finish that. Now there's going to be a little bit of delay here, of drag, we say, because this is finished in 10 hours, and then this one, in theory, if it wasn't for task 2, it could finish 3 hours earlier. Now task 6, it takes 1 hour, but it has to be done after task 2 and task 3, so we add 1 to 13 and add 1 to 10, and we take the largest one of those. That's 14. And so let's keep going with this. I think you probably get the idea. Task 4, we add 6 hours to 13, we get 19. Task 7, we add 1 hour to 19, and we get 20. And task 8, we add 2 hours to both 16 and 2 hours to 19, and we take the biggest one, because that's the bottleneck. And finally, task 9, we add 5 hours to 21 and to 20, and we take the biggest one, and we get 26. So this is an example. This set of tasks will take 26 hours, and then the shortest possible completion time, this 26, you can trace back. Let's do that along some path. So this 26 came from some path along here back to the first task. So I think, let me see, so 5 plus 2 is 7, 8, 9, 10, plus 6 is 16, plus 7 is, oh, that's only 23. So I guess there's a longer task. Let's maybe go up here. 5 plus 1 is 6, plus 6 is 12, plus 6 is 18, plus 7 is 25. So somewhere there should be, oh, I know, let's go up this way. So often it's not clear where that is. So there's 5 hours plus 2 is 7, plus 6 is 13, plus 6 is 19, plus 7 is 26. So this is the so-called critical path through the network, which is the bottleneck. So this is an example of something that's called dynamic programming, where you keep track of information at every step of the way, and ideally you would keep track of some extra information so you could trace back this path. But those are details that I don't really want to get into in this class. I basically just want to show you how things like partially ordered sets really do come up in practice. Not really about the method and the details of how to solve this particular type of scheduling problem. I will conclude with one more example from Wikipedia. I'm not going to actually do this, but I want to show you what one of these annotated posets might look like. So here's a collection of tasks, as before, with durations on each one. And here we are keeping track of things like the earliest possible start of this task, the earliest possible finish, and the latest possible start and the latest possible finish. And we will use those to compute these values in later tasks. And we also keep track of things like the drag, which, remember, corresponds with some sort of delay amount, so some inefficiency. And again, this is one example, but in the real world, these things might have hundreds, if not thousands, of nodes. And so solving this is something you just can't do by hand. But fortunately, there are efficient computer algorithms to solve these. And I think we're going to leave it there. See you next time.